Okay, so
Then you will say
we can maybe make a start. So welcome to the second session of this workshop. Our speaker is going to be Professor Haavard Rue, who's a professor of statistics and applied math, as well as being the chair of statistics here at KAUST. He's obviously well known for R-INLA and is a current holder of has been awarded the Guy Silver Medal in Statistics from the Royal Statistical Society, and he's going to be speaking on group cross-validation in R-INLA. Please take it away, and thank you, Haavard, for coming.
Right. Oh, it's better, huh? Okay, very good. Okay, topic, cross-validation. This is one of the things that suddenly you find yourself doing work on cross-validation. If you asked me 5 years ago, no, never. But you end up facing that we have an issue, and we have to solve it, or then we get Saddam to solve it. So this is about his main topic for his thesis. So he's defending now end of May, but it's group cross-validation. This has been a long kind of journey because this topic, it's so simple and so difficult at the same time. Okay, it's simple because everybody kind of knows what it is and know how to use it, we think. And difficult because there is no clear foundation. Okay, so let's just recap what it is. Cross-validation is like you have your data, you take a part of it to validate your kind of prediction. Prediction is whatever you fitted from the other part of the data. And very often we don't have too much data, so we like to do these things by kind of using the data that we have. We cannot kind of afford to put aside 1/4 of the data just to validate the model. I'd rather use that to estimate my model better, and then I could maybe use a smaller set, and then you can kind of think you can recycle this on different kind of subset, and as soon as you do different subsets, you will compute some kind of average or how you do these different subsets. Okay. So what's the purpose of cross-validation? As essentially say something about the predictive performance. Okay. It's easy to have a model that fit well to the data. It's worse to have a model that kind of predict a new data point well. These are two different things. So you estimate the predicted performance, and then the question is, what do you do with it? Very often you do model selection, sometimes also model calibration to kind of adjust the model, so you have kind of good kind of predictive stuff. So the kind of procedure is super simple. You split the data into training and test set. You estimate the model from the training, and it's working. And then you predict the data, and you evaluate the prediction for the data in the kind of in test set or in validation set. Okay, very simple. Of course, you need to compute a score. You have to say, is this a good prediction or is it bad? How good is it? That's another question. Okay, from this you can compute a score, and then you kind of repeat this thing to compute some kind of average or expected score. Okay, so then you got a number. You have another model. You do the same thing, and then you say, well, is my number bigger than yours? And then this is essentially how it comes. It's two common strategies for this cross-validation, and one is this leave one out. This is a common one. Okay, you take one data point out. Essentially, you fit the model for the rest of the except that one. You try to predict that one again. This is called leave one out cross-validation. Very often we kind of compute the density for the data point that we want to predict, or we do the log of these things. And then you essentially do that for all of the data points. And then you sum the logs, so you do some kind of geometric mean, and you get a number. The other one that many think is more fancy is what's called a k-fold cross-validation. It's very, okay, we come to this, why this is quite fun. Okay, so you take the data, instead of doing one by one, you divide it in 10 chunks. And you estimate model from the 9/10 for the data, you predict the 1/10. So either you compute some kind of, again, some kind of score for the prediction, so either the log density for joint, or you just sum them up. Okay, so it's essentially the same thing, but instead you do 1 and 1, you can do chunks. And this kind of makes sense if you are in a situation where if you take data out, you really have to refit the model. Okay, so that will reduce the number of times you have to refit the model. This is very well. The problem comes in that cross-validation. They don't have a clear foundation. There is no derivation in cross-validation leading to this is what we should do. It's kind of a heuristic. And you see, okay, but there are some math saying this goes well. Yes. You let something go to infinity, and it turns out it doesn't matter whether you remove a point or not. So these things are the same limit, and that's it. So if you believe the asymptotics, you don't have to remove any point. You can just use the data and just evaluate how good the model is fitting the data. Okay, and still we do this. But the other hidden assumption is that essentially X is kind of covariate. Variables you need to kind of explain, put into the model, and data, they are kind of independent. This is the frequent assumption you have in regression. You have covariance data independent. Many kind of classification problems. You collect a lot of images, do all these things. You think of them coming from one kind of big population. You just do a random sample. In this kind of sense, with this assumption, there are two. We need. Okay, this is getting tricky. Okay, we need predictions to make sense. Okay, if you have IID, everything comes from one population. If you have, it's the one thing you haven't observed, it makes sense to use other samples to kind of try to predict that. Okay, so in that sense, there is some kind of well-defined limit. You just sample more and more samples from the same population distribution, and then you let this n go to infinity, and we have a clear limit. It's very easy to forget about this because almost all models we can use it for have dependence. So it means that this kind of assumptions are broken. Okay. So what do we mean by the models have dependence? It's simply that it's not this case, a complement of this case. You have some kind of dependence, and then this is what you have. So what do you do in this case? So what's the problem? The main problem is not very clear what to do at all. Okay, because if you want to make prediction for a model where you have kind of dependence, you can think for simplicity, you have kind of a time series. You have kind of to define what you mean by your prediction. Okay, you have another kind of model. There are different kind of terms. What do we mean by prediction in that sense? Prediction is supposed to be a new data point that is collecting, you know? So how do you collect a new data point? Are you expanding the area you're looking at? Are you looking finer and finer in this area? Do you look at another time point to the future? Are you looking for a new subpopulation? Okay, so the point is that what is prediction is no longer there. Okay. Of course, this what you mean by prediction depends on what you're going to use the model for. Okay, so different people will have different ways of using the model. So it means that the whole concept of what is prediction in this kind of model depends on this is your choice. Okay. The other thing, there is no n go to infinity limit in this case. In many of these kind of models, you can let n, there are many n's. Okay, there are many people. You can let the number of people go to infinity. You can, for each person, you can make the number of measurements for that person go to infinity. Okay, and there are many other ways you can let things go to infinity. So there is no kind of asymptotic limit. Okay. Okay, if you don't, you can always create one, but it's not very useful. The point is that leave one out, it's still used. Okay, I'm not saying that it's wrong, it's still useful. But the point is that in these cases where you have dependence, we're talking more about evaluating interpolation instead of evaluating prediction. Okay. Interpolation is much easier. You know, predicting a new data point into some kind of area where you don't have too much data is much harder than to in an area where the model is, you have data, everything is fine. You have missing point. This is not much easier. Yes. Correct. 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 Okay, it's coming. It's coming. Okay. Yeah, you can always, okay, I think this will become clear in the next thing. The other thing is that this k-fold cross-validation, so just taking the data and divide it into 10 kind of random parts. You might think it is a good idea. This is actually much worse than doing leave one out. When you have dependence, because then you have no control over what you're doing, you can have 2 points, data points close by. These behave very differently that you remove. This behaves very differently than 2 data points far away. Okay. So this is even worse. Maybe this will answer a little bit questions. So for example, for time series, just to take a very simple case, you have time series model. The common prediction scenarios you're looking at is essentially to predict into the future. Okay, so the pure time series is quite fine. So you have the time from 1 to t. You want to predict like 3 steps into the future. Okay, and then you can do that for this time series. You can increase it a little bit. You can always try to predict, and then you have observed the kind of the data 3 steps afterwards in the future. Okay. This is what I mean by more interpolation, and this is essentially not what we do. So this is leave one out cross-validation, but the real prediction scenario for time series is essentially doing prediction in the future. Okay, and just to do some math, and then you'll see that this is very different. Okay, autoregressive order 1, leave one out cross-validation. You take 1 point out, and you have essentially the rest. Okay, so then you see the variance is okay. The variance is a constant, 1 divided by 1 plus phi squared. This is the lag 1 correlation. Usually this is quite high because it's your purpose of doing time series. Okay, and the other one is the expected value is phi 1 plus divided by 1 plus phi squared, and then the mean. if you think to it, the interesting case is like this phi is like 0.85, 0.9, quite high. Then you see that almost whatever you do, you will do really well. Okay. And then you see another feature that is very easy here, just to do phi equal to 1. This is the limiting case. It's an intrinsic model. So this will correspond to random walk 1. It's a very local model because this interpolation task will tend to favor kind of models that are local. If you do random walk 1, it's horrible for prediction because the prediction is just constant. Okay. If you then go to a real prediction scenario, predicting into the future, you see that the variance depends much more on phi, and also the expected value depends much more on phi. Okay, so here you see you can really, if you're evaluating this, you can really get to the kind of the inverse and really get the value for phi, if you like. Okay, so here you have real sensitivity for what you want to do for prediction in terms of the parameterization. For interpolation, you easily get into the case that whatever you do, it doesn't matter. Okay. And then you say, yeah, what's new about this thing? Nothing. All of this is common knowledge. At the same time, not that common. So this is a paper 10 years ago, 2016. This is in ecology, talking about maybe doing prediction tasks for different kind of models. If you have like spatial model, maybe you have to divide the data into kind of chunks in terms of area. If you have time series, maybe you have to divide it in chunks with respect to time. If you have some kind of grouping, this is like clusters of data that have similar properties. Maybe we should do that instead. And then they have some kind of hierarchical models, but some of this with a name I cannot pronounce. Okay. The point is that this is known, but it's not that known. Okay. And his point is that it's not much used. Okay, it should be. Always, if you go to the literature, almost no one doing something beyond leave one out cross-validation. Okay. So how to proceed? The point is that this is easy. Conceptually, this is easy. Okay. This is a frustrating thing. It's so easy and difficult and undefined and unclear at the same time. It's easy. You have a model, doesn't matter what it is, you have your model. For every data point, you have to define what would be a likely prediction scenario for you to predict that data point. Maybe you want to kind of remove some other data points to make it more like prediction. Okay. To define a set, the group that you want to kind of remove is a set of indexes. You remove all the data points in that kind of set, and then you want to predict yi. Of course, you have to make sure that the choices you do are aligned with what you want to use it for. Okay, so what your meaning is, what your interpretation is about prediction for that specific model. And then you compute the prediction, you're evaluating the data point, you're refitting maybe the model after removing this kind of some chunks of data, and you do that for all I. Okay. The point is, as soon as you start doing this, you end up saying, "God, this is annoying. This is actually a lot of work," you know. And you end up that, for many cases, you cannot really do this in a very well way. Okay. Life is complicated. You don't know. You have two effects. Is this stronger than the other one? Should I have more neighbors in that direction than in the other direction? What about the other things? You know, it's very, very complicated. And the other thing is that it's a lot of work. First to define the thing, and then you actually have to compute it. is even. If you're using software where you have some kind of excess to leave one out cross-validation, or you know how to do it, you've done it before, then why shouldn't you do that? You know, others are doing it. I can do it. So I think we often fall into that kind of trap, is that it's so convenient just to do that. So, and it's not too bad. No, it's not really bad. It's just that you can do better. Okay. It's a little bit the same as choosing priors. You know, if you're reading books about priors, yeah, you're choosing priors, so it corresponds to your prior beliefs. And then you end up finding someone doing a similar model. You take the prior, you make a reference to them, and you blame them if it goes wrong. Okay. It's a little bit the same thing. You know, it's so easy to talk about, but when it comes to kind of actual doing it, very hard. Okay. Okay, so we can. It's kind of a no-brainer. We need something automatic, semi-automatic, that do sensible choices in reasonable time. Okay. So how should we do that? We aim to computing this thing, and we want to kind of predict yi. And gi is a set. Of course, it contains I, so we have to remove that data point. We want to kind of predict. So we want to kind of excluding data that is too close to yi. Okay. We want to kind of emulate prediction. So you like in the sense of time series, you see, okay, we know what we should do. We take a chunk of time, we want to predict the future, and we do a new set of time, predict the future, and so on. Okay. This makes you easily end up a situation where you have to refit the model again and again. Okay, because you're not working with the same model as a bit removing data. You're essentially working with a sequence of models that are increasing in size. Okay, but in a way, if you have time series, if you want to predict here, you can kind of remove a few points before and after. And this is more or less same as doing prediction. Okay, maybe if you remove 4 points to the left and to the right, this corresponds to it predicting 3 time steps in the future. Okay, it's not exactly the same, but it's almost. So what should this kind of method do? If suppose we have a way of doing this, or some kind of test cases we can kind of try this on. And one way is the kind of multi-level model. This is very, very tricky. It's a singular model. Okay, so this is like a regression model. Essentially, you have in country, you have regions in the country. Every region has cities. Within every city, there are schools. Within the schools, there are levels. And with these levels, there can be classes, or school have different classes. Okay, so you have this kind of hierarchical structure. So if I want to kind of predict as a y12, I want to predict the performance of a one kid in that class. It seems reasonable that I can use the other school, but I cannot use other kids in the same class. Okay, so in this sense, I kind of want to, if I want to predict y12, the natural group is the class that is in. The other thing that this say that the model itself say that every kid in a class has the same correlation between each other. And every kid in that class has the same correlation to every kid in another class somewhere else. Okay, so you have this natural kind of singularity. You have exact correlation one, some pairs, and the other is not. Okay, so it's a little bit harder than normal. You think that correlation is a continuous thing, so we never get one. Here in case you have a lot of ones. Okay, so here, at least when the model has a such clear structure, we can kind of define the groups using the prior, essentially prior conditional. Okay. As soon as you connect data to this kind of exact correlation goes away, and it makes it impossible to automatically construct groups that represent this kind of multi-level model. Another thing, if you only have spatial data, it's very easy to use spatial data because it's so easy to illustrate. Okay, if you want to predict a black point, then you just remove neighbors. Okay, how much should you remove, or is it what to do about these things? Here, maybe we would just use the procedure, we just fit the model, and for every data point, we remove someone else. Okay, so this is a quite easy problem where we just want to kind of remove data points that are close by. Okay, but both these cases are very kind of idealistic, simple. As soon as you make them a little bit more realistic, the intuition we have is easily breakable. Okay, so how should we move on? And of course, if we want to make something useful, because this is getting a bit technical, you have to do exact calculations because you have a lot of singularities in this kind of dependence. Okay, so we're over to this kind of class of latent Gaussian models. Okay, so we are working for the class of models we are doing for this R-INLA kind of project. So we have some kind of data that are conditionally independent. They relate to the linear predictor, how we want to kind of essentially a regression model. And this class of models we consider is kind of Gaussian. Okay, time series models, spatial model, random effects model, measurement error models. All these kind of things is part Gaussian process. Okay, then we have some hyperparameters that is on the top. So this is a kind of generic structure. You might think this is looking very restrictive. I can invent something more general. Yeah, I'm sure you can. This is very, very useful. It's enormous amount of models that follows this. This is the main workhouse in kind of applied stat. So how can we do these things? The point is here, we're talking about data are close in some way. The point is that we cannot work with distances between data. Data doesn't have the right structure. Talking about this, there is a lot of Gaussianity, so we have to work with correlation. For correlation to make sense, we have to work with variables that is essentially Gaussian, maybe a little bit skewed. Okay, otherwise the concept of correlation doesn't really apply. Okay, so we can work with not for the data, but for the latent variable that predict the data. Okay, so we can work with the correlation between the linear predictor for this data point I want to predict and any other linear predictor. Okay, so you can kind of just order them, all this kind of correlation for fixed I, starting with larger ones, okay, and go down. And then at some point you say that, yeah, maybe I want to remove 5, whatever 5 is, and then you take the 5 largest ones. These are the ones that linear predictor kind of is most useful for kind of predicting, say something about the ith data points. Then you have the problem that correlations can they will be identical. The point is that if you have this kind of issue, just like for the class example, if you remove one, essentially you have to remove everyone else that has the same, where the correlation is 1 with this guy. Okay. So as soon as you take one kid out of school from that class, you have to take the whole class out. Okay. So it means that we're talking more about level sets and how many level sets we should kind of exclude. If you're kind of using 4 and in the time series example, we kind of, you say that if I'm here, the closest correlation is the next one, but also the previous one. Okay, so they will have the same correlation. So if I take about remove that one, also have to remove the previous one. Okay. So if the level set is 4, you take where you are, take one more, 2, and then 3. So that's 4. But because we have this kind of ident, they are perfectly correlated, we also have to take the other side. Okay. So then automatically we get this kind of thing that we like to have. There are different variations. So essentially you can use essentially the prior or the posterior. So this corresponds if the model have a very, very regular structure where you essentially know the groups, you want to recreate them. We switch on the prior. Otherwise, we do this for the posterior. Okay. And we essentially, it's all this correlation depends on the hyperparameters. And yeah, we have to, we fix the hyperparameter at the mode to get the unique set of groups. Okay. Just to give you an example, just to see what this could be, this is like data that you have on regions. So on the left, we have the groups, the group that you have for the area, and that is in black. You want to predict that one, you remove the gray ones. Okay. So this is the prior on the left and the posterior on the right, and they are more or less the same. Here is another point. This model also contains a covariant. So on the left, you have kind of similar structure, but on the right, you have a lot of other things going on. You see, suddenly you get kind of neighbors somewhere else. Okay. Again, this intuition that kind of breaks down, because as soon as you have a large covariate in one region, the dependence between two kind of linear predictors essentially come from that covariate, and not from the kind of a spatial mode. Okay, so the other region is similar, is just region where you have high value of the same kind of covariate. Okay. You see, this is picking up this kind of dependence very completely automatic. And then you say, does this make sense? Exactly. If you don't do this, it doesn't make sense. Okay. It's just the way we are so kind of preoccupied by some of this. It have to be this thing. No, it shouldn't. It's all about dependence, and it doesn't matter where it comes from. Here is another one. It's a data in space and time. Here are different kind of measurement stations. Okay, so for every station, you measure the wind. Of course, the stations are fixed. It's a thing. And you measure this in high resolution in time. You want to kind of, again, do prediction. And here is like, there are some, if we own, here is mainly a model that has a model for space and time. It's like a non-simple model. It's a proper model. You have two types of dependence. You have dependence in space at the same time, and you have dependence in time for the same space, or depending in time for another location. Okay. So what should we use? And then if you think, if you're going far north, there is quite far between the stations. So it means that the time element becoming more important. So you see that these kind of dotted lines also mean that you have neighbors at that station for a different time point. Okay, if you go to more roughly Edinburgh, you're halfway, so it's only few of those who have a neighbor to a different time point for another station. But as soon as you're getting more and more dense stations, like in essentially around London, then everything that matters is what happened at that same time point. Okay, and this is happening automatically. It's beautiful. Okay, so we can zoom out here. You have two of those for different time points. Here's only one, and for London there is. Okay, So how we actually do these things? The point is that we have to do all the computation without having to refit the model again and again and again and again. We have to do the one fit and then compute correction to that kind of fit because we want to remove some data. Okay. Of course, this is possible. It's straightforward. It's pretty tedious. Okay. And there are a lot of corner cases that require some attention, and you don't see the cases before things fail or things are not accurate enough, and you go in and you kind of fix it, you close that, you try another one and try to break it. Okay. For those who are known to R-INLA, then the scheme is a little different from what was original there for the normal cross-validation. And it's, of course, is using extensively this latent Gaussian model framework. It's essentially without that, it's very, very hard to do these computations. Okay. So the number of level set, if you set that parameter to -1, we get exactly leave-one out cross-validation. Okay. So here are the things, is that you have data with some likelihood, so the latent model is integrated out. The point is that there is. You can take for the hyperparameter, you can take whatever you have, the posterior for that one with the data where chunks of data is removed out, is whatever it is without removing, and you have to divide by this conditional distribution for the data that you have removed. Okay, so this is the thing. You do that for the linear predictor, you do the same for hyperparameters, and of course you need to, in general, you need to kind of merge all these together, so you need to integrate out this. It is a bit messy, but it is done. Okay. Yeah, it's probably a phone, it's just like that. Yes. Yes, just my Doris is probably asking what is the number of level sets he's following on soon. And this is essentially the big elephant in the room. It's like if it's easy if you remove one data point, it's well defined. I remove one data point, I want to predict it. If I need to remove someone else, how many should I choose? Okay. There is no correct value. There is no way to kind of estimate this value. If you like 3, then you can use 3. If you rather prefer 4, then you can use 4. There is no value, but when something is not kind of well defined in this sense, what you do all of them. You know, you do 1, 2, 3, 4, maybe it's fine. There's no point of removing too much because you're removing the predictive power of the model. There is no one value that is best. I think it's important to use something else than 1. Okay, at least improving leave one out cross-validation. You're doing something better than you normally would do, and that's good. Okay, there is no optimal choice. Of course, you do this and you see, do they all kind of make sense? Do they agree internally? Of course, you have this kind of scores. You can have interpretation like if you have 2 models, the model 1 with k equal 3 correspond to model 2 with k equal 4. Okay, so the one can do better prediction, same kind of quality after removing more of the data. The bottom line is leave one out cross-validation should not be the default. So what is then better? 2. Okay, if I had to set a value, I would set 2. Why? Because it's never extreme. And the other thing, it's better than leave 1 out. Okay. So at least we improving the default. Okay. If you want to do something else, then it's fine. Where is it? Okay, I'll be quick on the last part. So how is this implement? How do you use it? The point is you fit the model and then you can start asking about cross-validation. So this is how we implement, because it makes life easier, because really you want to kind of fit the model and then you want to kind of evaluate it afterwards. You can kind of fit it, you can compute cross-validation for one by just passing in the results. And you compute automatically the groups, logarithmic utility, and also provide information. You want to do things manually yourself. Okay. If you're not used to this kind of thing, I'm not sure if this is making sense. Okay. You can do is you easily find yourself, you do this in a loop, you do all cross-validation from 1 to 5. Just do a loop, compute all these cross-validations. You can compute the average score. Of course, the prediction score would go lower and lower. This is in this model is not, it's a little weird one, but it's okay. Okay. The thing is that if you have different models, you simply want to have a good one to define the groups, and you want to take the groups you find there to evaluate another model. So of course here you can kind of feed in manual groups, just take the results from one, fit to evaluate the cross-validation in another one. Okay. So all this is well done, it's all done. Okay. Just to summarize, do a quick summary. Leave one out cross-validation is, I'm not saying it's not valid, I'm saying it's not that valid. Okay, for dependent data and models. And this is more serious than we think. Interpolation is different from prediction. And I think this is a little bit why there is a lot of use of these very flexible models, run over this very, very spline, locally based model, because it fits well with cross-validation, because it fits well within the interpolation framework. If you're using that for prediction in the future, that's another story. Okay. If you want to do it better, then leave one out, and you have to do it yourself manually. This is a tedious task. Okay. We can automate these things pretty good. It seems to do the right thing again and again. Okay, it do a sensible thing. If you say no, I can do it better. Yeah, please. Point is that very often this is so tedious. Then if you have to do it, you will simply not do it. So then it's better to have something quick. Do with that. I think do a pretty good job. I think it's do better than you normally would do yourself. Okay. In R-INLA, this is very easy to do. Of course, you can feed this in. If you have a specific task, you can use this kind of tool to kind of define it and then simplify your life. Okay. Thank you.
Thank you. Thank you for the talk, Haavard. Do we have any other questions, speaker?
Thank you for nice talk. Is it possible somehow to build surrogate, cheap surrogate, and so sample from surrogate and make sample set bigger?
Samples in the way, what you mean by samples?
No, if we have not enough data, we can build surrogate, so cheap model of our, and then sample from this, so generate data from this surrogate.
Yeah, this is, in this class of model that we usually do this for, this is not particular, we are not often in that situation, okay? And you can do this pretty quick in any case, okay? So it's maybe if you take these ideas over to your field, maybe you have to revise it and do it a little bit different.
Mm-hmm. And another question. I just thinking about this data set which we receive from Mark Genton and his Computation. It's 2 million data set from satellite. He removed a subset, and we should do prediction. And you suggested, for example, to split it in k subdomains. But what about hierarchical approach? So you first take just let's say 10% of this, then 20% of this, then 40%, and so you have hierarchy. So coarse approximation of your data, then average approximation, and then very fine. And
there is a limit how much data you want to remove, you know. The point is that you want to kind of keep the predicting power in the model, at the same time do some kind of reasonable prediction. Okay, I don't think you need to remove that many points, you know. The thing is that if you're doing exact refit of the model, you can think you can do prediction in that corner and that corner and that corner and that corner, and they are more or less independent. So you can get 4 results for the cost of 1. Okay, so I think this is removing chunks of data is more like a computational thing. You can speed up the computations, but as soon as you remove a little bit, there is no point of removing more, because you're ending up predicting just like essentially predicting the mean.
And the last, did you think about to clean the data? So, for example, 2 points which are very close to each other.
No, this is happening totally automatic. You know.
Okay.
Yeah, there is no, you don't need this.
Thank you.
Do you have any further questions? Is there anything online? Do you know? Or... All right. If not, let's thank Haavard again. Thank you so much, Haavard.